Hey everybody, Dr. Retzig here. This is our second video in section 16.3. It surrounds three theorems that lay the theoretical foundation for the practical aspects of 16.3. Let's get started. Okay, so we have three theorems. Let's write them down in an appropriate order. You can compare and contrast this to the order in the section in the book. All right, here we go. Theorem 1. Theorem 1 says that the line integral of a vector field f dot dr comes out 0 around every closed loop in whatever the domain D is, if and only if the vector field is conservative on D. Okay, let's talk about all the words in here. Okay, f dot dr, we understand that that's a line integral of a vector field. Closed loop, that means a curve C whose initial and terminal points are the same. That double arrow symbol, that means if and only if. So that means A implies B and B implies A. In other words, the two statements on either side of that double arrow symbol are equivalent to each other. And remember, to say that f is conservative on D is simply to say that the value of the line integral on any path is independent of the path and depends only on the endpoints. There are no special hypotheses on the domain D. All we know is the curves in question, the closed loops in this theorem, they all belong to D. But nothing about connectedness, nothing about simply connectedness. This theorem is just relating what happens on closed loops to F being conservative. Okay, so I'm going to box this up. The rationale for the theorem is that if you have a closed loop like that, well, you could break it up somewhere in the middle, and you could name that point A and that point B. And think of your closed loop as two separate curves. This is curve 1, this is curve 2. And so the integral over the whole thing is the integral over C1 plus the integral over C2. But that's integral over C1, take away integral over C2 hat, where C2 hat simply reverses C2. And now you can see C2 hat and C1 have the same starting and ending point. So if F is conservative, then they come out the same. So their difference is 0. And if the difference is 0, they come out the same. And so F is conservative. So that's more or less the idea behind the proof. Okay, so f dot dr's integral comes out 0 around every closed loop if and only if F is conservative on D. Okay. Next theorem. Next theorem. This one we have a few more hypotheses that we need to be careful with. Okay, so suppose you have a vector field that's 3D. So at every point x, y, z in 3D space, there is some vector. And the first component of that vector depends on x, y, and z. We can name it big M. The second component of that vector also depends on x, y, and z. We can name it big N. And the last component also depends on x, y, and z. We can name it big P. So let that big F be given by the vector m, n, p, where the ingredients in each component, the m function, the n function, and the p function are continuous on the open, connected domain D. Okay, so suppose that's all the case. You have this 3D vector field. The components are continuous on an open connected domain D. All right, here's the statement of the theorem. Then this vector field, big F, is conservative if and only if big F is somebody's gradient. So if and only if big F is gradient little f for some differentiable function little f. Okay, let's box that up and then let's talk about some of the hypotheses we have going here. So effectively, this in the blue box is theorem 2. Okay, so this one, we have to be a little more careful with the hypotheses. So let's put hypotheses underlined in red. We need the components to be continuous. We need the domain to be open and connected. Okay, with all of those hypotheses in place, to test whether or not a vector field is conservative is the same as to decide whether or not the vector field is somebody's gradient. Okay, so looking at the first two theorems, the first one says to test whether something's conservative, really you only have to look at closed loops, and you don't have to know anything special about the domain or anything. Just if it's 0 around every closed loop, then you're good, it's conservative. The second theorem says, okay, if you put a few more hypotheses in, namely that the component functions of your 3D vector field are continuous and that the domain is open and connected, then to decide if it's conservative is the same as to decide if it's got to be somebody's gradient. Okay, now the proof of that theorem, theorem 2 here, this is on page 923 in the book, and it's not so bad. Basically, if you are known to be somebody's gradient, and by the fundamental theorem of line integrals, you're automatically conservative because the value of the line integral comes out only dependent on the start and end point. So this direction of the statement, this direction, if you are somebody's gradient, then you are conservative. That's straightforward because of the fundamental theorem. This direction, that's the harder direction. Because in that direction, all you get to do is assume that big F is conservative, and then you have to somehow argue that it's some little f's gradient. And I mean, where are you going to pull this little f out of? Just out of thin air. Whose gradient? Wait, you don't even have a formula for big F. How could you possibly argue that big F is somebody's gradient? Well, you just define an anchor point to be the initial point of any line integral involving big F, and then you define little f to be what the line integral comes out to from that anchor point to some other point B. And then you make some argument that that little f is in fact differentiable and its gradient is big F. Okay, so read up on that proof on page 923 if you're interested. Come to class with questions. All right, so we have two theorems. First theorem, f is conservative if and only if it's 0 around every closed loop. If and only if its line integral is 0 around every closed loop. Second theorem, a little more refined. Under the right hypotheses, f is conservative if and only if f is somebody's gradient. All right, here we go. Third and final theorem. Third and final theorem. Hypotheses start out looking similar to theorem 2. So again, let big F be a 3D vector field. So first component, something depending on x, y, and z, name it big M. Second component, something else depending on x, y, and z, name it big N. Last component, something else depending on x, y, and z, name it big P. Where M, N, and P. All right, now we have to be a little more demanding here in order for theorem 3 to go through. We need big M, N, and P to be a little better than simply continuous as they were in theorem 2 above. We need them to be what's called C1. Now C1 is just math shorthand for all of their first partials needing to be continuous. So dm dx, dm dy, dm dz, dn dx, dn dy, dn dz, dp dx, dp dy, dp dz, all of those need to be continuous. That's what C1 means. On an open, connected, and simply connected domain D. So you can see we're being a little more restrictive with the domain as well. If you have all of that in place, then finally you get the actual practical test for whether the vector field F is conservative. Then big F is conservative if and only if three things. dp dy has to come out the same as dn dz, and dm dz has to come out the same as dp dx, and dn dx has to come out the same as dm dy. So now being conservative boils down to those three equations being true. Let's box that up, and then let's talk about where this comes from. Okay, hypotheses first. Note, in this one, hypotheses are slightly more restrictive. The component functions m, n, and p have to be better than just continuous. They have to be C1. All of their first partials have to be continuous. The domain has to be better than open and connected. It has to be open, connected, and simply connected. I believe your book leaves out the word open. I feel like any domain on which we're going to discuss differentiability needs to be open because I don't want to think about derivatives at boundary points. So I'm putting open in. Okay, but certainly connected and simply connected are required. Now, under all of those technical hypotheses, you get this pretty clean statement about what it means for f to be conservative. You simply apply this test. Some people call this the components test. Now let's talk about why the test might be what it is. So focus here. If you are hoping that big F ends up conservative, then by theorem 2, you're hoping that big F ends up being someone's gradient. In other words, you would need big M to be df dx, and you would need big N to be df dy, and you would need big P to be df dz. So to be conservative, you would need M, N, and P to be the partials of some function little f like that. Now, focus on this piece. Requiring that dp dy equal dn dz, we'll look back at P. P was already df dz. So dp dy is the mixed partial df with respect to y and z. Now, look at n. If you're hoping n is already df dy, then dn dz is the mixed partial of f, dz dy. But by Clairaut's theorem, those are supposed to match. The mixed partials should match. So if p and n are already going to be a first partial, then the partials of p and n are second partials, and the second partials have to match by Clairaut all the way back in chapter 14. Similarly, look at this piece. If m is supposed to be df dx and p is supposed to be df dz, then m's z partial better match p's x partial by Clairaut. Okay, think about the last piece. If n is already supposed to be df dy and m is already supposed to be df dx, then n's x partial better match m's y partial, again by Clairaut. So the deep connection here is all the way back to the agreement of the mixed partials given by Clairaut's theorem. That is essentially one direction of the proof. The other direction of the proof follows from what's called Stokes' theorem, which would be at the end of a normal Math 241. Stokes' theorem is some sort of 3D version of the theorem we're going to develop in 16.4. And Stokes' theorem implies the other direction of this proof. So for now, you need to know the statements of these theorems. One remark here on theorem 3 before we go. If you were considering, in the special case, where f is a 2D vector field, so m depends only on x and y, second component n depends only on x and y, and no other components. Then look at all those conditions on those partials. When there is no z and there is no p, then you can see the only one of those equations with no z's and no p's in it is this one. So the 2D test is even easier. You just have to make that n's x partial matches m's y partial. All right, so this is particularly easy in the 2D situation. Okay, that's it for the theorems. We have one more day in 16.3. during which we will practice. You have some suggested problems, come to class with questions, and we'll continue getting 16.3 dialed in. See you next time.